What is Stokes theorem? We said when we did Green theorem, we stated the theorem, right? We said, if you can still remember, we said by definition, Green theorem states that it relates a line integral to what? A double integral, right? Similarly for Stokes theorem, right? By definition, Stokes theorem relates a line integral of a vector field f around a closed curve C equals the flux of the rotation or coil of f through any surface bounded by C. Through any surface bounded by C. Now, let's explain what it means. We want to understand this theorem now. We are going to understand it theoretically, practically, and diagrammatically. Before we proceed, let's go back to Green's theorem. Green's theorem, by definition, we said this is my Green's theorem. Say this is x. Say this is what? Y. You have a closed curve, right? This closed curve, this is your boundary. And this is your what? This region is what? R, right? We said it relates the line integral, meaning when we say line integral, meaning work done around this part, right? To the double integral. Do you understand what I'm saying? Now, in case of Stokes theorem is now telling you that instead of relating your line integral to double integral, we are relating it to what? We are relating it to surface integral around the closed curve C. This is the C.
Equals to the flux.
Equals to the what? Flux of the rotation or coil
through any surface bounded by C.
Through any surface bounded by C. Expected, we are going to have, I believe you understand, you know what coil means. When we say coil rotation, when we did Green theorem, we already explained that. We are saying we are imagining that there's a rotation inside our river. So we are not saying out of this river, there's rotation around the river. So you are just taking 2 points. Say point P and point Q. Let's say you have point P and you have point Q. So you are differentiating this. P and Q, they are vector field. Meaning P is a function of what? X and Y. Q is a function of what? X and Y. So you are differentiating this guy with respect to what? X, and you are differentiating this guy with respect to what? Y. So to get your coil that has occurred inside this river, meaning the summation of this, that is the P over the X minus the Q over the Y. And this is the idea behind what? Green's theorem. This is the idea behind Green's theorem. Now, still that same rotation or coil, we are now relating it to surface integral bounded by what? C. But you understand what it means when we start solving. You understand what it means. Now, practically, by definition, what I just want to do is that the analogy that I'll be giving, relate it to the theory itself. Are you getting me? The analogy that I'll be giving, relate it to the theory itself. Now, by theory, we said, just listen, you don't need to write. Stokes theorem relates a line integral of a vector field F around a closed curve C equals to the flux of the rotation. When we say rotation, meaning coil, equals to the flux of the rotation of F through any surface bounded by C. Through any surface bounded by C. Meaning, you are relating that line integral to any surface of that shape. To any surface of that shape. Now, doing a practical analogy, imagine a fan where air is circulating along the edges. In this case now, the edges is what? The edges. In Stokes theorem, we have two terms there. We have line integral, and the what? Surface integral. So me doing any practical explanation, I just want to locate what's my line integral in that analogy and what's my surface integral in that analogy. Now, for the last time, imagine a fan where air is rotating along the edges. The movement of the air is along the boundary. In that case, the boundary, will it be the line integral or the surface integral? The line integral. And this is what you are seeing here. Let's say you have this fan rotating. The air of this fan now is along the edges of this blade. Meaning, in this case, the edges is the what? Line integral. And if this is your line integral, you have different surfaces in this part, true or false? That circle stuff is a surface. The three blades, they are surface, right? Meaning, you want to use Stokes theorem, you can take any of these surfaces. Do you understand what I'm saying? Yes. You can take any of these surfaces to justify the whole surface. In this case, I'm having that circle that I'm seeing, I'm having the three blades. So it's either I take any of these blades or I take the circle to analyze the whole fan. And that's what Stokes theorem is saying. Now, relate it to the theory that you've written down. Are they correlating? Are they correlating? And that's Stokes theorem. That's Stokes theorem. So with practical analogy, I believe you understand it better. Instead of working around the boundary C, just like the way we always do in Green Theorem, you know, when we want to solve Green Theorem, solving the line integral, what do we do? From A to B, from B to C, from C to D, from D to A, right? I'm working around the what? Boundary. Now, we now said, instead of working around the boundary C and adding up all the tiny changes in the vector field, right? You know, this is it. From here, let's say you are given a question under Green Theorem. Say this is A, say this is B, say this is C, say this is D. You know, of course, this is my what? C1, this is my what? C2, this is my what? C3, this is my what? C4. Now, I want to ask this simple question. Me moving along A to B, what's the purpose? You know, I want to implement this formula which says that integral P dx plus Q dy, and it will be given your function of P and Q will be given, right? Now, I'm now asking this simple question. Me walking from A to B, what's the purpose? What do I want to know? The what? The derivative. We've forgotten this term. You know, it's still the basis of what we've learned that we are applying. I'll help you with that. Now, from here, we said, my second analogy, based on my second practical explanation, that's what brought us to this. We now said, instead of working around the boundary C and adding up tiny changes in the vector field, right? You know, P and Q, they are your vector field. P and Q are your vector field. Now, say you are given a question under Green Theorem. I'll move from A to B. I'll move from B to C, C to D, D to C. Now, me moving from A to B, what's the purpose? I want to know my derivative, right? I want to know my derivative. Me knowing my derivative, meaning I need a function of x and I need a function of what? Y. I need the function of x along A to B. I need the function of x and y along A to B. I also need the function of x and y along B to C. Similarly, C to D and what? D to A. Now, listen. Instead of working around the boundary C and adding up the tiny changes in the vector field, right? You know, that's what we are doing in Green Theorem. We are moving around the what? Boundary. Now, in Stokes theorem, we are not saying instead of working around the boundary C and adding up the tiny changes in the vector field, we can look at the whole surface inside the boundary and calculate how much rotation or coil that exists there. From here, diagrammatically, we've looked at Stokes theorem by theory and by what? Practical. You've seen the first analogy and the second analogy. Now, diagrammatically, because this, we are going to use more of this when it comes to questions. If you look at Stokes theorem, theoretically, practically, now diagrammatically. Now, what this means is that from here, and what we've learned in terms of the theory, in terms of the practical, that's what we just want to implement here. And this is what we'll be using throughout. Given any question, this is what we'll be using throughout. Now, the whole idea here is that, you know, from here, looking at this diagram, my Cartesian coordinate, do I have it as 2D or 3D? 3D. When we say 3D, meaning X, Y, Z. So what it means is that Stokes theorem is an extension of Green's theorem. That is, Green's theorem is 2D, whereas Stokes theorem is what? 3D. Now, you know, my interest here is my surface. Looking at this diagram, how many surface do I have? 3. Yeah, I have 3 surface. But let's say 2. Let's say we have 2 surface. Now, this surface, let's say you are giving this question, and this surface is defined as cylinder. Then you draw a diagram. With this diagram, I'm just asking this question. Am I seeing another surface apart from the one given to me in the question? Yes. I'm seeing. And what is this surface? the one down, right? And this one you can relate it to what? Circle. Let's say this is circle, right? Meaning I'm giving a question, that question has a surface, and in that surface of that question I'm still having another surface. Do you understand? Meaning you can now apply what Stokes Theorem is saying, meaning that you can use any surface, any convenient surface. That is either I go with the given surface or the new surface that I have for that question, which in this case is what? This D. Do you understand me at all? Now from here, you also observe that the same boundary that S is having, say this is the first surface, call this one, say this is the second surface, call this 2. You observe that the first surface, which is 1, and the second surface, which is 2, they are having the same boundary, right? They are having the same boundary. Meaning, given a question, say you want to solve that question using Stokes Theorem. By the time you identify that, okay, this question, I can use either this surface or this surface, you must also consider these surfaces, are they having the same boundary? If they are having the same boundary, you can make use of any of these surfaces. Do you understand what I'm saying? And by what we've seen here, in the given question, this is the surface, and this given question, if this is the surface, I'm seeing another surface which I can relate to what? Circle. Now let's say I'm not using this one, I want to use this one. The question is, both of them, are they having the same boundary? If yes, I can implement this. If otherwise, I'll stay with this. Do you understand what I'm saying? That's it. As far as they are having what? The same boundary. Can you now see that we are already applying what Green Theorem states diagrammatically? Mathematically, when you say line integral, from the idea of vector calculus, you know that line integral, this is what it simply means. F integral f dot dr. Integral f dot dr. Now, what Stokes Theorem is telling us again, and we are going to see that when we start solving. Another thing that Stokes Theorem is telling us is that, given a question, instead of reusing this line integral, I can make use of what? Stokes Theorem, which should be easier for me. Do you understand me? Instead of me using this line integral, I can make use of what? Stokes Theorem, which will be what? Easier for me. Based on what we've done so far, when we did Green Theorem, between the line integral and the double integral, which one is easier? The double integral, similarly to Stokes Theorem. Instead of using the line integral, I can make use of what? The Stokes Theorem, which is where coil is coming from. Now, by Stokes Theorem, we have integral f dot dr is equal to the double integral of coil of f dot ds. Coil of f of ds. Now, from here, let's define this. We said we have integral, this is C, this is your surface. Now let's define this. I have double integral S coil of f ds. Now from here, look up. From here, this ds, it varies. In the sense that depending on the surface you are using. Are you getting me? This is my Stokes Theorem, right? This is the left hand side. This is the left hand side. And this is the what? Right hand side. Now let's take this left hand side. From here, this left hand side, it varies. When I say varies, meaning this guy, this ds, is not constant. It's always change. And it is changing based on the surface you are using. Based on what? The surface you are using. Let's say you are using cylinder and you are using hemisphere. It is obvious that the surface of hemisphere is different from the surface of what? Cylinder. Similarly, if it was circle I'm using, the surfaces are what? Different. So now you are saying this ds, it depends on your surface that you are using. Meaning the surface that you are concluding to use in the given question, that's the ds you use. You understand? Now, meaning this right hand side, you can write it as double integral coil of f dot n ds. Now let's define each term one by one. Let's define this coil, and let's define what m is, and let's define what the s means. This is the right hand side of Stokes Theorem. Stokes Theorem is telling us that given a complex integral, instead of me using my FDR, which is the formula for line integral. I can make use of what? Stokes Theorem, which will make my work easier. Now, we now said this Stokes Theorem formula, which is the right hand side, you can still have it as this. The question is, why is this one transforming to this? It's transforming based on the surface you are using. Based on the what? Surface you are using. Now, with this same diagram, say that this is my surface. This is my surface. From what we've explained previously, is either I use this surface or this surface. Let's say you are using this surface. This surface now, what it means is that this surface, I'm going to calculate the n of this surface. I'm going to calculate the ds of this surface. So this is why I'm having this formula as this. Let's say I'm using this surface. I'm going to know the n of this surface, and I'm going to know the ds of this surface. Now, it depends. The surface might be a flat surface or a curved surface. Now, if it is a flat surface, the way you are going to calculate the n is different from the way you are going to calculate the n if it's a what? Curved surface. Now, when we say flat surface, meaning 2D. When we say curved surface, meaning what? 3D. By formula, to calculate the n of your flat surface, this first one, the n of this first one, meaning the normal vector of this first one, this is the formula, r over the magnitude of r. But this one, the cross product of the surface, this is the surface. This surface is in x, y, z, meaning the cross product of this surface. Now you observe something. This is my formula for cross product of this curved surface. You are seeing s, meaning the surface with respect to x multiplied by the surface with respect to y. Why am I not including z? Meaning I'm expressing z as a function of x and y. So what that means is that given any surface, your axis, your z must be expressed in what? Function of x and y. So this comes to what we call parametrization. What do I call it? Parametrization. Now, by parametrization, when we give Green Theorem, you've seen how it works. The whole idea of parametrization is that instead of me using my shortcut method, I'll make use of what? Formula. Just not, there's nothing like shortcut when it comes to Stokes Theorem. Are you getting it? You are using your full parametrization. Now, when we say parametrization, given different surface, I must know the parametrization of each surface. Given different surface, I must know the what? Parametrization of each surfaces. Now, let's define Stokes Theorem. The left hand side and the right hand side. Now, this n is called the normal vector. We've seen that. There's what we call, though you can do your readings further, there's what we call right hand rule. Right hand rule, meaning based on the orientation you are going. Just that, generally, okay, this is it. For this guy now, we already know that this is the formula for n. For this one, we already know that this is the formula for n. Now, when you are doing when you are solving your R, your R is just you converting a scalar to a vector. Your R is what? You converting a scalar to a vector. A scalar to a vector is what? Type. Now, that's where you'll be seeing in question, you'll be seeing that z is equals to 0. Z is equals to 3. Abi? I don't know if you've checked those, what you call Stokes Theorem. You'll be seeing that z is equals to 0. Z is equals to 3. Now, it should be stated here that z, just not, if this is my z, if this is my x, if this is my y, this is my origin, right? This is my origin. Now let's say that from here, let's say we want to draw our graph. This is 0, right? Then I have my number 1 in ascending order. 1, 2, 3, 4. Are you getting me? 0, 1, 2, 3, 4. Now let's say that the question says that z is equals to 2. Z is equals to 2. Meaning at the top, right? At the top of x axis. Meaning at this point. So let's say you have z is equals to 2. Right? Let's say you have z is equals to 2. Meaning what you are going to do with this is a scalar. This is a scalar. You see the same thing as you writing 0. Let's define this scalar as saying phi is equals to what? 0x plus 2 plus 0y plus 2z, right? I'm giving that in the question, I'm giving z is equals to 2, meaning it's at the top. And what I want to use, what I want to do with this guy is that I want to convert this scalar given to a vector field. So I'm now saying let's define it with a particular parameter. I'm using phi. You might decide to use p, right? So let's use p now, meaning p is equal to 0x plus 0y plus 2z, right? What's that? Which is still the same thing as writing p equals to what? 2z. What you have here is still equivalent to this. Your 0x and 0y has no effect. You are just writing it in a nicer way to show that you have x, y, and z. Now, let's say that we are doing drag, die, and coil. You are giving this scalar. The question says that convert this scalar given to a vector field. Convert this given scalar to a vector field. You are giving p is equals to 0x plus 0y plus 2z. Let's convert this to what? To vector. Meaning the derivative, right? I'm differentiating this with respect to x, differentiate this with respect to y, differentiate this with respect to what? Z. So let's do that. Meaning I have the grad of p is equals to 0, right? 0i plus 0j plus what? 2k. Therefore, grad of p is equals to what? 2k. Let me get the magnitude. By magnitude of p, what do I have? I have square root of 2 square, meaning square root of 4, which is equals to what? 2. Therefore, n, which is equals to r over magnitude of r, implies your r means this guy, right? 2k over what? 2. Therefore, 2 cancel out. What do you have? K. You have k. Now, what this means is that if you have a flat surface, if your z is at the top, generally it will be k. You take it as k. Do you understand me? If it is at the top, when I say top, meaning z is above 0. Let's say z is starting from 1, 2, 3, 4, meaning it takes k. By the time you solve it, you still get k. But what if z is equal to 0 or is at the bottom? It takes what? Negative k. Are you getting me? Negative k. This is when my surface is flat. But when my surface is curved, how do I get this n? Now, n means the surface with respect to x multiplied by the surface with respect to y. Now the question is, okay, no, let me start solving, you see it. But let me just let's just see the concept behind it. Now what this means is that given a surface, you express x, y, z in terms of what? You express z in terms of what? X and y. Then you are going to do the partial derivative of the surface with respect to s and the partial derivative of the surface with respect to y. Then you are going to do the cross product. You are going to do the cross product. So this is what basically this n is telling you. That's what n means. N is the normal. N is the normal. Now let's take that. Everything that I am still doing this morning is the introduction of Stokes Theorem. Introduction of Stokes Theorem. We are doing the introduction. We've done the introduction by stating the theorem. We've done the introduction by doing practical analogy. We've done the introduction by what? Diagram. By diagram. So we doing all this. It will be easier for us when it comes to solving. When it comes to solving, it will be easier for me. It won't stress me. I didn't know that, okay, this is what I'm working with. So that's the purpose of all this introduction. Now, number one, let's define Stokes Theorem. Let's define the mathematical formula, the left hand side and the right hand side. The surface. We want to define the surface and the boundary. We want to define the surface and the boundary. Now, by definition, well, we've said everything so far. You can not necessarily to write. You can just listen, understand. But if you want to write, you can still write. Now, what surface and boundary is telling us is that the surface S is given by now we are defining the surface and the boundary. We now said the surface S is given by the surface x is defined as a function of x, y, z. The surface s is defined as a function of the surface x is defined as a function of x, y, z, where z is a function of x and y. Therefore, our surface, we have it as x, y, f of x comma what, y, where this is what, z, where this is what, z. And always our surface is projected to the x and y plane. And always our surface is projected to the x and y plane. And always the surface x is projected to the x and y plane. Also take note, the orientation C follows a counterclockwise direction. The orientation C follows a counterclockwise direction. Now, let's see what that means. Let's see what it means. The first one, surface and what? Surface and boundary. S, which is my surface, is given as a function of what? X, y, z. Where z is a function of x, y. Where z is a function of x, y. Meaning, call this one, say this is 1. Meaning you can have 1 as 2, right? By the time you substitute this z, you have it as what? 2. This will bring us back to this place. When we define the normal here, we said the normal is the surface of x. We are differentiating the surface with respect to x, multiply. Okay, we differentiated the surface with respect to x and y, then we multiply. Can you see how it works? It's not like you are not having any function of z here. Just because we said z is always a function of x and y. So this is it. That's what surface means. And we also say that this same surface is always projected to the what? X and what? Y plane. Now look at your Cartesian coordinate. This is x, this is y, this is z. If this is your surface, the other surface that you have, where is it present? X and y plane. That's what it means. And by orientation, meaning the orientation of your surface follows the same orientation this same surface has. You understand? Now the next one, normal vector n, normal vector n, normal vector. Normal vector n. The arrow, I said it previously, I said it before. When we say normal vector, it's meaning this arrow. Now, normal vector n, the arrow represents the outward normal to the surface x. This normal is determined using the right hand rule. This normal is determined using the right hand rule. So you can read on that right hand rule. What right hand rule just tells us is that just like if you are going in a counterclockwise direction, if this your normal is pointing upward, meaning positive, inward, meaning downward. So if you are going in a counterclockwise direction, meaning it will point outward. If you are going clockwise, it will point towards inward, and it follows your right hand rule. It follows your right hand rule. There is explanation to that, but we are not going to be looking at it. Alright, now the next one, the surface D. The surface D, meaning this projected surface. Number 3, the surface D. The surface D. D is a projection of x. D is a projection of x onto the x and y plane. D is a projection of x onto the x and y plane. D, this guy, this D. The x. D is a projection of x, this x, onto the x and y plane. The curve C is the boundary of D. The curve C is the boundary of D. The curve C is the boundary of D, and its orientation, the curve C is the boundary of D and is oriented consistently, and it is oriented consistently, and it is oriented consistently with C to satisfy Stokes theorem, and it is oriented consistently with C to satisfy Stokes theorem, and it is what? Oriented with C to satisfy Stokes theorem. Do you know what it means? Do you know what that means? Okay, now let me come again for the last time. We said satisfy Stokes theorem, meaning Stokes theorem is satisfied. How is Stokes theorem satisfied? You go back to the theorem now. For the last time, we said D is a projection. Sorry, yeah, it's wrong. D is a projection of X onto the XY plane. The curve C is the boundary of D and is oriented consistently with C to satisfy what? Stokes theorem. What that means, what it simply means is that the boundary of the given surface with the boundary of the new surface, which is D, they are the same, meaning it is consistent. It is consistent, meaning it is satisfying Stokes theorem. Why? Because Stokes theorem says that you can choose any surface as far as the boundary is the same. As far as the boundary is the same. We've said that previously. So that's what it means. Also, your normal, take note. Your normal is always in the Z axis. Your normal is always in the Z axis. Your normal is always in the Z axis. Your normal is always on the Z axis. Upward normal, positive. Upward normal, positive Z. Downward normal, Are you agreeing with this? He said upward normal, always Z. When we say Z by magnitude, K. Downward normal, negative K. Do you agree with it? Why? Because we explained, right? When we said upward, meaning Z is equal to 2, 3. And we've seen that by formula that we end up getting what? K, meaning positive Z. If it is below, it will be what? Negative. We use more of this in Gauss theorem. We use this in Gauss theorem, right? Now, from here, I guess that's all. And if it is positive, also take note. If your normal is positive, meaning the direction. If your normal is positive, meaning C is a counterclockwise direction. C is moving in a counterclockwise direction. If your normal is positive, C is moving in a counterclockwise direction. If it is negative, it is moving in a downward direction. This is everything when it comes to Stokes theorem. This is everything when it comes to, when it comes to introduction specifically. This is all we need to know when it comes to what? Introduction. So far, we've seen Stokes theorem theoretically, practically, and diagrammatically. Now, for the last one, F is a vector field. F is a vector field. F is a vector field which will always be given in xi plus yj plus zk. I'm going to find the coil of F by formula. What's called ijk partial d over dx, d over dy, d over what? dz, x, y, z. Then perform your what? Determinant. Perform your determinant. So this is all when it comes to Stokes theorem. Now, the next aspect, giving a question, interpret your question. What did I say? Given a question, my ability to interpret my question on Stokes theorem. That's what we want to look at now. We've done all the theory aspects. Now, I'm giving a question on Stokes theorem. This given question, what am I doing here? What do I need here? Right? Now, let's take down.